When speaking about Bayesian statistics, we often hear about probabilistic programming. But what is it? Which languages and libraries allow you to program probabilistically? When is Stan, PyMC, Pyro, or any other probabilistic programming language most appropriate for your project? And when should you even use Bayesian libraries instead of non-Bayesian tools like Statsmodels or Scikit-learn? Colin Carroll will answer all these questions for you. Colin is a machine learning researcher and software engineer who's notably worked on modeling risk in the airline industry and building NLP-powered search infrastructure for finance. He is also an active contributor to open source, particularly to the popular PyMC3 and ArviZ libraries. Having studied geometric measure theory at Rice University, Colin was bound to walk in the woods with Pete the Pup, who was there when we recorded, by the way, and to launch balloons into near space in his spare time. Hey folks, just a note before beginning, we had a long conversation with Colin and it was so interesting that I decided to break it into 2 parts. So you'll get the next part in 2 weeks, where we'll talk about how to implement and communicate Bayesian models in industry. So bottom line, you get 2 for the price of 1. Anyway, on to the show now. This is Learning Bayesian Statistics, Episode 3, Part 1, recorded October 18, 2019. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the project, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.anvil.app. That's learnbayesstats.anvil.app.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly
Colin Carroll, welcome to Learning Bayesian Statistics.
Thank you, Alex.
Yeah, I'm really thrilled you're taking the time for that. It's a real pleasure having you on the show. And actually, we're coming to you live from Somerville, Massachusetts. So you're the first guest I get to see in person through the magic of human interactions. So thank you very much for hosting me. So I guess we're gonna dig right in. And I think listeners from the introduction to the show, they will have guessed that you do a lot of things. Actually, how did you get to these topics? How did you first get introduced to Python and Bayesian methods?
Yeah, so that was actually sort of a 2-step process. I actually did my graduate work in pure mathematics, which a working definition of pure math is not using a computer while you're doing that. So I got out of grad school hardly ever touching a computer. And the first step was getting into Python. I found a data science job that was pretty hot at the time. And it was a job that gave me enough space to sort of learn how to use Python over the course of my first 2 to 3 years working there, which was really wonderful. Bayesian statistics sort of came afterwards. It just so happens that it lives pretty close to the field of study I did. I studied measure theory in grad school, but I studied very general measure theory, right? So the difference between probabilities and general measures is that probabilities have measure 1. You measure the entire space. In some sense, it's easier in that you're not worried about these infinite measures, but in another sense, it's much harder in that you can say a lot more things about it. There's a lot more results about it. And so I started getting into that just about a year and a half ago, after I was already pretty embedded in sort of data science and Python. And I can tell you a little about how that started.
Yeah. Actually, I'm really interested in that because you said 1 year and a half ago, right?
Yeah, I think 1.5, 2 years started contributing.
Pretty recent.
Yeah, I had seen PyMC2 early on in my data science sort of career, and it was sort of fun to work with. This gives you random variables as sort of computer variables, and that was nice to be able to manipulate them in that way. But I had never done any serious work with that. And I came back and I saw PyMC3 about 2 years ago. At the time, I had a 90-minute commute each way. Yeah, it was quite a travel, and most of this was on a train. I had limited internet access. This turned into really good concentration time for me, and I started sort of taking a look at a bunch of different open source libraries, and PyMC3 was one of them. At the time, the test suite for PyMC3 was tests more in the sense of the statistical tests rather than unit tests. And so each one would pass with very high probability. But at the scale that PyMC3 was at the time, usually it was probably 50-50 whether the entire test suite would pass or not. And so one of the first contributions I made was just improving the test suite, making it reproducible, and making sure it passed every time. And I think the reason that I stuck around was that the other contributors were so friendly and so sort of immediately helpful. Within 30 minutes of submitting a pull request, they said thank you, they merged it, and I felt like really proud the next day at work. I was like, wow, I'm making a difference in like this open source software. That sort of got me going on that. And I got into a nice rhythm after a while where I could do all the code changes in the morning and make the pull request in the evening. And so each day I was sort of making one pull request during my journey on the train.
Right. That's pretty efficient. Well done.
Yeah. It was a fun time. There's a lot that I don't miss of that commute, but there is a little that I do miss.
Yes. So actually you went into the PyMC project by programming or informatics, or I guess.
It was sort of felt a little backwards in that here I am, I did pure math. I'd always viewed myself as a very theoretical person, and my first contributions were of a software engineering type.
Yeah.
At that time, my job title was software engineer, which was interesting.
Okay.
Though the company was a financial tech startup and later made one of the bigger machine learning exits in the startup world, but they hired everyone as a software engineer, and I was doing a lot of infrastructure type work.
Okay. And were you trained for this type of work, or because from your background, you didn't really say software engineering was in your educational curriculum?
That was a really interesting start. They actually sort of tossed me into building this search infrastructure the first week, and I went and I picked up the Elasticsearch book. And I'm not sure if you've ever read the Harry Potter series. The Elasticsearch book, it's something like 700 pages, and it is pretty easy reading, but I felt like Hermione telling the other engineers that it's as though they'd never even read, Elasticsearch, the definitive guide. and it has a lot of really good tidbits in it about how to get started. But yeah, it was a lot of self-teaching. And then I think that sort of looking at the unit tests, I'd sort of just been taught how to write good unit tests and how useful they can be in a software engineering standpoint. So I think that was like a really useful lesson. I sort of had the fervor of the recently converted. So I was interested in unit testing all the things at the time. I've softened a little bit, but I still find like the test suite of a project says a lot about the health of a project.
Yes. Plus, when you see the depth of the PyMC3 code base, at least today, you really need some automated tests, I guess.
I obviously think the world of PyMC3, but it is a pretty old code base. It has had a lot of contributors. And part of the difficulty, I think, of having, as I was saying, my first experience was getting a very fast merge. And I think this implies a lot of trust on the part of the maintainers, on the part of Chris Vansbeck, Thomas Vicky. I think we're merging that stuff then. I think that implies a lot of trust, and part of that trust will mean merging bad code. One of my early pull requests was rewriting the no U-turn sampler to be iterative, and my refactoring was entirely wrong. So there was about a week where if you were working off of master, you had this garbage sampler that gave you garbage samples.
But it's okay. I mean, the nut sampler is not that used.
I know. Well, after about a week, it was Kyle Beauchamp he opened a pull request and said, hey, everything's wrong. If you try to sample from a normal distribution, you don't get a normal distribution. It's just like the most basic of tests. So we rolled that back, and it's only been recently that I've seen actual implementations of an iterative no U-turn sampler. Both the NumPyro team and Jung Peng over on the TensorFlow probability team have both introduced them within the last 6 months. Looking at those attempts, they were much more involved and much more nuanced than what I was trying to do at the time. But yeah, so this means that something like PyMC3 has a lot of code that's not beautifully engineered, and that's good and bad. It means that there's a lot of place for people to go do code cleanup. There's a lot of place for documentation, but also it means that there's a lot of possibility for mistakes, and sometimes it's hard to read and be familiar with the code base. So I think tests are important. I think good linting and good automation is really important.
Yeah, clearly. And actually, when you realized that you made these mistakes about the nuts sampler PR, how did you feel? I mean, personally, were you like, oh my God, what have I done?
Yeah.
And then you were like, oh, I don't know if I can do another PR anytime soon, or how was it?
Yeah, well, I think it certainly made me a lot more careful about what I was doing. It had sort of been, I think I'd been making a lot of lower pressure pull requests, and then all of a sudden I figured, I'd been to school for a long time. I can probably do anything I want. And it turns out that you do need to study these new subjects that you might be going into. I encourage people who are working with open source projects to not set their sights low because of that sort of story, but maybe emphasize in the pull request that it will need a careful review or some extra testing or something. But yeah, I think that is where I sort of got more into the academic side of Bayesian statistics, started reading a lot more of the papers, making that pull request. I had gone through the no U-turn sampler paper very carefully, but this sort of had me going through again. And actually, the end result of that pull request was, after we reverted it, I went back through and with a lot of help from Adrian Seibel, we went and refactored the no U-turn sampler from PyMC3. And this allowed us to make a lot of improvements to the core algorithm and sort of start keeping up with all the great improvements Stan is doing. And the interesting thing, if you go back in the Git history far enough, the original no U-turn sampler in PyMC3 looks exactly like it is in the paper from Gellman and Hoffman, up to the Greek-looking variable names. There is one incredible function. I believe it took 11 inputs and gave 8 outputs, and it was called recursively. And all the inputs were between 1 and 2 letters of variable names. So you had no idea what was going into this or coming out of it, unless you had already memorized what all the variable names stood for and everything. So I think one of the biggest helps is we refactored all that into using like named tuples. And so you'd go and look at like tree.left branch or tree.right branch, and you could refer to things the way that computer programmers are more used to. And so now you can go through and read it. And I think that's one of the best ways to learn how the no U-turn sampler works is by looking at the PyMC3 code base now. I think it's a very beautiful implementation now.
Oh, okay, good to know. We could speak about this. These PRs and open source contribution a long time, but unfortunately we're on the clock. So I guess it's a good time to go into actually, why did you go into these Bayesian methods and why do you use them today in your everyday workflow, I guess?
Yeah, that's a really good question. I think that's still a question that I think a lot of people wonder about. And I think a lot of people also have the wrong answer about. So these Bayesian methods let you write down much more interesting models and much more nuanced models than the basic ones you might get in Scikit-learn. But on the other hand, you have to think really carefully about the models that you're making and what you're going to do with these models once you finish. I think Michael Betancourt has a great line in one of his talks that if you're using Bayesian methods, it's because you care about the uncertainty in your parameters. I think that's a good thing to reflect upon. So the right reason to use these methods is not necessarily for prediction, though there have been use cases I've seen where the prediction is as good or better than with your scikit-learn or even with neural nets. But the reason that you're doing this is to quantify some sort of uncertainty in your parameters. And so you should think about it if you have a loss function that cares about some sort of latent parameter that you can't look at, or just if you want to be able to estimate some latent parameter and you want to be able to say like how confident you are in those. So I think that's why I still use these methods today. One thing I'll point to is when I was working in this flight insurance role, so we were concerned about what flights would be canceled, let's say. And one naive way of going about this is saying, let's say 5% of all flights are canceled in any given day. Right. And so you can back out from there pretty quickly how much you need to charge to cover any given flight. Right. You should charge 5% of how much the flight costs. But we all sort of know that when a flight gets canceled in like Charlotte, then there's a much higher chance of like planes being delayed getting to New York City. And the flights get delayed out of New York City. So there's this rich correlation structure, and the correlations lead to fat tails, which means that if you really look at this, your worst day is going to be much, much worse than 5%.
Yeah.
That's really what you need to worry about. That's what's going to bankrupt you at the end of the day. So in that case, we do care about these uncertainty in your parameters, because what we care about is this 99th percentile. What's the 1 in 100 days going to be? Because you'll have 3 of those days every year. So we wanted to know about our worst case risk and make sure that we weren't going to go out of business just on those couple of days.
That's the thing also I really love about Bayesian methods. And it's actually also why I dug into it. It's because you can really think about the model and having something really tailored to your situation. And it's harder to think about it and to implement it in the first place. But when you do that, you get a lot for free and you get a really more interesting model that you can really squeeze for insights, I guess. And also you can say where the model probably doesn't work, which is really interesting too, I guess. When we speak about Bayesian statistics, we often hear about probabilistic programming. And so I wonder how you would define probabilistic programming, because when I first encountered this term, it was really opaque for me what it meant.
This is another really good question. I really love these questions that seem basic but end up being pretty deep. And so probabilistic programming is an academic discipline. Tom Rainforth at Oxford just published his thesis, which I think he describes as secretly a textbook on probabilistic programming. And the first probably 60 pages is a really nice read on what probabilistic programming is. That's sort of both from an academic viewpoint and like a pretty like helpful way just to think about where the field is. And roughly he talks about having some way of defining a joint probability distribution, some way of conditioning on data, and then some way of sampling. And there exists sort of general probabilistic programming languages, and there are more or less general ones, right? Stan sort of famously doesn't accept discrete parameters. PyMC3 probably shouldn't, but it does. But then there's all these other sort of self-referential type probabilistic programmings that in theory you should be able to write and sample and condition. And so you do, from an academic point of view, there is this hierarchy of probabilistic programming languages. But I think really the way we use this in practice is just as a way of using random variables as variables in a program. And so you can add them together, you can multiply them, you can use them as parameters in other random variables. And so I think that's sort of a fine working knowledge for someone who's aiming to use this in industry or in everyday work.
Yeah, okay. Yeah, I get that. And so from what you say, I guess that to do probabilistic programming, you have to use a probabilistic programming language. So as you are a PyMC core dev, I guess you use PyMC quite a lot. So maybe it's a good time to explain what PyMC3 is to our audience.
Yeah, sorry, I've been referring to PyMC3 without defining it at all.
Yeah, but it's good. It gives kind of an overview, and now we're digging into it.
Yeah, so PyMC3 is a Python library, and it lets you define a statistical model. And under the hood, this really just means we're putting together a joint probability distribution. But you end up writing this in a pretty natural way. So you can write down like linear regression. You know, your data is coming into the model outside. Your weights, you're just going to say, are going to be normally distributed, perhaps. And then you can add on some normally distributed noise. And then you can condition this on your observations. So you have some targets and you can condition them. And PyMC3 lets you write that down sort of the way you would like to write that down, which is just by saying that, like, hey, my weights are normally distributed. I don't know what they are. My targets are normally distributed around data times the weights. And I do know what those are. Here are the targets. And then PyMC3 will sort of run this backwards inference using MCMC. So it'll go and try to recover what your actual weights might have been, recover what the posterior distribution of your weights were given that data. And so this is a nice way of working. It's quite flexible. It lets you write down a whole host of models quite flexibly. A number of interesting projects built on top of PyMC3, which I think is maybe the right place for a lot of interesting projects. And just sort of as we talk about probabilistic programming, I would mention that like I've seen at least two, one by Nicole Carson and one by Daniel Amazit, doing Scikit-learn in PyMC3. So what they're doing is they're implementing logistic regression, linear regression, and all various regularizations using PyMC3 because PyMC3 is sort of more general, lets you write down these probability distributions, and then just following the Scikit-learn APIs that you can go and fit them.
That's called PyMC-learn, right?
There's one that's PyMC-learn, and then there's Daniel's package. I can't remember the name of Nicole's.
Oh, yeah. But we'll put that in the show note
awesome.
for people. You. And actually, so why would you do that? I mean, using the Scikit-learn API, but with PyMC under the hood?
Yeah, so when you use PyMC3 under the hood, what you're going to get is these full posteriors over the parameters that went into your model. So for linear regression, instead of just getting a point estimate for your weights, what you're going to get is a full estimate on what your weights are. And so if there's some particular weight that it's important that it's less than 0, you could actually go grab this full posterior, look at how many samples are less than 0 and say, hey, we've got a 82% chance that this third parameter is less than 0. And this might have real business value to you.
Yeah, okay. But I guess that these types of projects like PyMC-learn would be... What's interesting is that for people that are already using and used to the Scikit-learn API to be able to build their models with PyMC under the hood, right? Because if you're using PyMC already in the first place, well, maybe it's not the good fit there, right?
Yeah, exactly.
Okay.
We talk a lot about how to make PyMC3 available to more people, and I think this is a really great approach. Another example, you see Sean Taylor's Prophet library. Yeah. And this is built on top of Stan, and it does this time series analysis, and you sort of don't even have to know that Stan is in there, but it goes and it extracts all of these parameters for you for free and gives you a pretty detailed analysis of your time series.
Yeah, that's awesome. I didn't get to use it yet, but I really want to do it because it looks amazing.
Yeah. So it's a joyful package, and I think there's a lot of interest there. I mean, so in the R ecosystem, there's also a lot of projects built around Stan that let you have pre-built models. Yeah. So I think that's an interesting future for tool building in the probabilistic programming world, is sort of hiding it behind an API so that the user doesn't necessarily need to know that there's a probabilistic program going on.
Yeah, but then how do you define the priors? Because I guess that with API like that, they define the priors for you, so you can't really adapt them, and for a really complicated model, that could be a problem, right?
Yeah, sure. And there's no great answer for that, or else we would have a very popular library that was Scikit-learn built on top of PyMC. One option you could imagine is much like in Scikit-learn, you might have a regularization argument that says it's going to be L1 or L2. You might imagine in a Bayesian library, you might say, what sort of residuals do I expect? Are they normal or are they student T distributed? Right. And so you give a finite number of options rather than giving sort of the full flexibility, which might be overwhelming and somewhat hard to fit.
Yeah, at least at the beginning for a user, that might be. Plus, it's really another mindset. I mean, when you're used to frequency analysis, then going fully Bayesian might be overwhelming. Yeah, I guess.
Yeah, exactly.
Yeah. But indeed, if you really want to get into that, in the end, you're going to have to go under the hood and do your prior yourself.
Yeah, I would expect that there are a few cases where someone like really loves fitting a linear regression using something like Profit and not wanting to go in and sort of tweak the parameters.
Yeah. Well, actually, you already answered this question a little, but I'm going to ask it formally so that you can give like a snapshot answer that I can use on Twitter in a short video. No, I'm kidding, but maybe the short answer of when would you use PyMC instead of non-Bayesian tools like Scikit-learn, for instance, or Statsmodels for the Python ecosystem, or even other package in the R ecosystem that do the same thing.
Sort of, if you can get away without using PyMC3, I would definitely do that. It takes a long time. It's going to tie up your computer for a while.
I guess the PyMC dev won't use that snapshot to advertise the package.
I know. I've got other really like complimentary things to say about Stan too, which is MCMC is a really expensive operation to do. And so you do want to be getting your money's worth out of all the computer time you're using. The thing it gives, especially for small models, is you can iterate very quickly and adjust your model a little bit, which is super powerful. So if you're comparing it to Scikit-learn, Scikit-learn is going to give you the maximum likelihood estimator for a lot of these models that you could write down instead in PyMC3. So this would be, in essence, going to PyMC3, you write down the model, you get all your samples, then you take the mean of all of your parameters, and that'll be what Scikit-learn would have told you. Not exactly the mean, something almost like the mean. If you're asking questions like, hey, is my number bigger than 0? You're not going to be able to do that with just the point estimate. Something like Statsmodels could tell you that for linear regression, right? Linear regression is a simple enough model that we can solve it pretty well with like math. If you're handy with linear algebra, you can say before you take the samples with PyMC3 what the samples will say. The problem is if you want to then go and say, maybe these residuals aren't normally distributed, maybe they're student T distributed. I think you can still do that by pen and paper, but now you're asking for a pretty good pen and paperist, and maybe it's cheaper just to spend 2 minutes to sample instead of writing sort of the linear algebra routines for each of these two different models. And then if you want to tweak it again even a little bit more, you sort of might not want to keep going back to the chalkboard in between each. So I think probabilistic programming language really wins once you're really iterating on your Bayesian model and iterating on the model that you care about, and you know that you care about the uncertainty in your parameters.
Yeah, okay. So that's really the big factor of decision would be, do you care about the uncertainty in the parameters?
Yeah, exactly. And I would also say that part of this advice is maybe you do your exploration using PyMC3, but then if you find out that linear regression, just OLS is your best answer, then pen and paper is also a great thing to do. So going back to using just pure NumPy afterwards for speed is also a great option.
Yeah, and actually, what's the difference between the different probabilistic programming languages that we talked about? What's the difference between PyMC, Stan, Pyro, and so on? And actually, you're a lot more qualified to do that than me, because I saw that you wrote a very interesting article in your blog about that, comparing, I think, 9 different PPLs.
It turned into 11 once I put it online. You know, you got people from other PPLs coming in and say, well, what about this one?
Yeah, exactly. And that's very interesting. And I put that in the show notes.
Yeah. So it's sort of funny. At conferences I go to, there's a lot of talk of like the rivalry between Stan and PyMC3. I don't think it's so controversial to say that Stan's about 3 months smarter and 30% faster than PyMC3. If those are the things that are most important to you, then like that's a great tool to use. PyMC3 takes a lot of cues from Stan. We try to follow pretty closely what they're doing because they're really good at what they do. I prefer PyMC3 for a lot of tasks because it's so well integrated into Python.
Yeah.
So I can write Python code like I'm used to writing Python code, and it works well with the rest of my libraries. Though I have used Stan, I have used PyStan. I think that they're also like really wonderful libraries. And I'm also glad that like Pyro, which seems to focus more on like variational inference, but they have been doing a lot of really interesting things. Like this NumPyro project has a no U-turn sampler implemented iteratively, and it's very neat. So I'm glad that they're around, and they're sort of taking a different tact to a lot of these approaches. I should back up and say that the area that I'm talking about here are libraries that can fit continuous probability models. And that's a very particular one. There's a lot of other domains of science that care more about discrete sampling. There's actually a group in Boston that works on gerrymandering. So this is led by Moon Duchin. They care deeply about discrete sampling. So they're looking at how precincts should be allocated to congressional districts. This is really hard. It feels a lot harder than this continuous sampling that we're doing. But in the space of continuous sampling, there's a number of projects that have popped up lately. And I think that everyone's learning from each other. And I think it's been really interesting.
Yeah.
I should say TensorFlow probability is another one that would be hard not to mention. So this is built on top of TensorFlow. They started off by implementing scipy.stats, but in TensorFlow. And so everything is differentiable. They've also been doing a really interesting approach in that everything they have done so far has been vectorized. And so it's a lot quicker to do independent experiments. These are chains in PyMC3. So this means that if you get 1,000 samples sampling from a single model, in PyMC3, we write our algorithm, and then we use a multiprocessing library to send this out to all the different processors on your computer. And so you'll get 4 or 8 at a time. On TensorFlow probability, this is all like matrix multiplication. So they can fit 1,000 different chains all at the same time, and it takes the same amount of time as if they did 4 chains all at once. And this is just sort of incredible. And I haven't thought about how to use 1,000 chains all at the same time. But there's a lot of really interesting experiments you can do all of a sudden. I mean, the Stan group wrote some papers recently on figuring out your effective sample size in R hat. These are ways of figuring out how well your MCMC sampling actually fit the posterior distribution. But they're expecting that you're using less than 20 chains most of the time. There are experiments that the TensorFlow probability team is putting out where they use 16,000 chains, right? And that's more samples than I usually take, but that's just every single sample. They have 16,000 versions of that sample. And so there's sort of a lot of really interesting work going on over in TensorFlow probability as well.
Yeah. Actually, if I'm not mistaken, PyMC4 will be based on TensorFlow probability, right?
Yeah, so that's what we're looking at right now.
So we'll talk about that at the end of the show, I guess, because we'll turn to the future. But maybe one follow-up question I had about what you say would be, when you're on a project, why would you use Stan instead of PyMC? Because you said that maybe your default would be PyMC because it's integrated in Python. And with Stan, you have to write in another language that's dedicated to the model. So when would you use Stan? And then when you use it, how do you use it? Because then your model, you have to save it somewhere and do the analysis, maybe in Python or R. How do you do that usually?
Yeah, so part of this will be like the company workflow, right? And so if we have a team where the majority is used to working in Stan, then I think it makes sense to continue working in Stan. Often by virtue of me being on the team, PyMC3 becomes like the thing that we're best at. And this has been fun using PyMC3 at work projects, is that since it's an open source software, we can submit features that would be useful to our company, and maybe it'd be useful to everyone else as well. It's always been fun, especially when companies support that sort of work. But yeah, if we do end up using Stan, actually one of the great joys of the last year has been this project ArviZ that we've been working on that aims to be a language visualization and diagnostic tool. And so by language agnostic, we mean that it works with Stan, it works with PyMC3, it works with Pyro. And so you can use sort of anything you want to do your inference. But then when you want to save it, when you want to analyze it, when you want to do things to it, you can use ArviZ. And so ArviZ comes with this system of data loaders. And so it'll take a model that you fit using PyStan, and it'll put it into X-array. X-array is essentially high-dimensional pandas. So you have labeled dimensions, you have labeled coordinates. And this is really helpful when you're doing Bayesian analysis, because dimensions sort of creep up on you there. I know you do this political analysis. And so maybe you have 50 districts that you're looking at. Each district has a name. Sort of want to remember which name goes with which dimension. And then maybe there's like a 2-dimensional you're estimating with each of those. It might be vote share for or against. So now you've got a 50 by 2 matrix. And then you take 1,000 samples of that. So now it's 50 by 2 by 1,000. And then you do 4 independent experiments or 4 chains. And so now you've got this 4-dimensional thing. NumPy has wonderful broadcasting, but it's really hard to figure out how to slice it exactly how you want to slice it. So it's much nicer if you can actually refer to these as like, hey, I want chain number 4, and it's going to be from the 12th arrondissement, and it's going to be this column. And so X-ray lets you do all that. X-Ray is also, it's built on top of HDF5, which is a nice system for saving these large files, and you can do efficient reads and writes. And it also plays nicely with Dask. I haven't done this, but you could imagine saving your analysis and then analyzing it actually over in Dask. It also has a bunch of nice plugins with Numba, which a Summer of Code student worked on and made a lot of things much more efficient going that way. It was sort of fun. They ended up having to rewrite everything very carefully because you can do like variance in one pass over a data set. You just have to be a little bit careful. In the same way, you can do a lot of these other numbers like effective sample size in fewer passes. Yeah, so we end up using ArviZ a lot in order to save all of our analysis. And then it doesn't matter what we originally fit the model with. We can use whatever we want afterwards.
Yeah, okay. That's great. Actually, do you use like Stan per se, or do you use the PyStan interface when you want to use Stan?
Yeah, I've always used the PyStan interface. Yeah. My first job out of grad school, I used R quite a bit. And probably if I was at another team that was using R, Stan would also be a great choice there. But since I'm using Python, I'll just use PyStan. And so I'll write the model in Stan and go from there.
Okay. So for listeners, PyStan, how does it work actually? Is it like an API to Stan, but you can write your model specification in Python?
Yeah, so Step Back Stan is a programming language on its own. I believe even GitHub recognizes that. And so if you have a project that has Stan code in it, it'll be 20% Python, 10% Stan, which is cool. But so Stan is a programming language, and PyStan will accept a Stan program, and it'll run that Stan program and give you an object where you can ask about sort of all the results of running that program. So your Stan program is just a string in this case. In that sense, it's somewhat easy to version control it, right? Because it's just another computer program.
Okay.
But you're going to be plugging it in and just running it out of Python. And so you're just calling Stan from Python. And then there's like friendly wrappers for getting the results of your inference afterwards.
Okay. But your model per se is written in Stan.
Yeah.
You write your string model in Stan that you pass to PyStan that then calls Stan.
Yes.
Okay.
Yes, exactly.
Yeah, okay. So you also have to know how to Stan works ideally.
I think PyMC3 took a lot of cues from Stan and tried to make it feel natural to a statistician on how to write what a model looks like. So it doesn't feel weird going back and forth.
Yeah, that's great. Hey guys, I hope you enjoyed part 1 of this interview, and I'm sure you now have a better idea of what probabilistic programming is and of what the landscape is in that regard. In 2 weeks, you'll meet again with Colin, but this time we're gonna look into how you can use probabilistic programming in your work. In particular, we'll see how to do it in industry and how then you can communicate and visualize your models with non-technical or executive people. So stay tuned and see you next time. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher, and visit learnbayesstats.envol.app for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.envol.app. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. Thanks so much for listening. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.